The next of our techniques of integration is dealing with something called trigonometric substitution. It's a variation on basic U substitution, but it's a very special kind, and it's deserving of its own special category, its own special section. And so that's what we're going to be talking about now. The basic, before we get to the actual process, we want to review a little bit about the Pythagorean Theorem. Because really, trigonometry, if you think about it, everything in trigonometry is just the Pythagorean Theorem gone crazy. And so, in order to understand what's happening with this process, we're going to take a look back at Pythagoras here a bit, and then throw in the trigonometric functions. And then with that, I think this becomes pretty straightforward. It's you need to keep your wits about you, but it's not brutally challenging here. Let's see if we can get from here to there. First off, if we have a right triangle, we know that Pythagoras applies to that. Now, we can say, suppose we know two of the sides of the triangle. There are three possibilities. Now, when I write my triangles for trigonometric substitution, and I'm going to do this the same way I learned this way back in basic, in my Calculus 2 course. So I'm going to do exactly the same thing that I did way back when. If you always draw the triangle the same way, it always leads you down the same path. The paths become familiar. You become used to what's happening, and it's much easier to get a feel for what's happening if you always do the process the same way. And I'll give you sort of some rules of thumb to follow, and that will help you, that you always get to the same basic kinds of integrals with our trigonometric substitution. So, one category is this. Suppose we know, and I'm going to pick just two variables to use at random. Suppose we know m and n. Suppose we know those two sides of the triangle. When I draw this triangle, I'm always going to draw it in this orientation, and I'm always going to put theta in the lower left-hand corner. Now, you'll see why that happens here in just a bit. But when you draw these triangles, my recommendation is there are other ways to do this, and you can memorize some things. There are other approaches to this. But what I'm going to take is a procedure that helps not only get the substitution correctly at the start, but there are some things when we finish that we need to translate. When we translate back to the original variable, it will help if we have these triangles drawn. So I'm going to do this the same way every time, and always put theta in the lower left corner. It can be done differently, but I'm always going to do the same thing. So, one possibility is you know these two sides. These are the legs. Another possibility is you might know the hypotenuse and the side that's opposite theta. Another possibility is you might know the hypotenuse and the side that's adjacent to theta. These are the only three possible possibilities on offer here. From the perspective of theta, you could know the two legs, you could know the hypotenuse on the opposite side, or the hypotenuse on the adjacent side. And in any one of these scenarios, now the question is, what is the value of this third side? Well, in this particular case, we know that if you take the leg squared plus the leg squared, that's the square of the hypotenuse. And so this value, notice, if I call this, just for a moment, I'm going to call this h for hypotenuse. Don't we know that the hypotenuse squared is m squared plus n squared? But I don't want hypotenuse squared. I want the hypotenuse to be the square root of m squared plus n squared. And that's what happens here. So, if the two legs are known, then the hypotenuse is expressed as this radical. Okay, now this case, suppose I call this S for side. I know that m squared is equal to s squared plus n squared. But now I know m and I know n. I want to find what s is equal to. So that means move this across. M squared is equal to, let me move this over to the side this way. We know that m squared minus n squared is equal to s. But again, I don't want s squared. I want s itself, and so you introduce the radical again. So in this scenario, this is m squared minus n squared. And then the third scenario is very similar to it. Call this the side now. We know that m squared is equal to s squared plus n squared. Again, move the n across, right? So that gives us, this implies that m squared minus n squared is equal to s squared. Again, we don't want s squared, so we introduce the radical. And so this side is the square root of m squared minus n squared. Now, there are some things to notice here. I'm going to rewrite this a little more neatly, get rid of this piece I don't need. All we're doing here is basic Pythagoras this is from way back in basic geometry. This is m squared minus n squared. So, what that means is, in any such triangle, there are three scenarios. One scenario is that the radical is the sum of two squares. Another scenario, in fact, both of these scenarios, it appears as though there are three. Really, there are three, but they manifest themselves in this view in just two. This is the square root of m squared minus n squared. Now, here's the key to notice. In both of these scenarios, notice that m was the hypotenuse. And so here's the rule, and this you can take to the bank, you can etch it in concrete, it's never going to change. In either of these two scenarios, whenever you have square minus square, whenever you have the square root of square minus square, that guarantees this is the hypotenuse. Do we see that? Whenever you have square minus square in either of two scenarios, m is the hypotenuse. However, whenever you have square plus square, notice m is not the hypotenuse, n is not the hypotenuse. What is the hypotenuse? The hypotenuse is the entire radical. If you have the square root of the sum of squares, then the entire radical is the hypotenuse. If, on the other hand, you have square minus square, then the hypotenuse is not m squared. The hypotenuse is just m by itself. So, what we've done here is we have the triangle, and we're seeing what we develop from it. What we do in the actual event, in the actual trigonometric substitution, it works precisely backwards. But armed with what we have so far, it becomes straightforward. Suppose we have, and let's just pick something out of the blue here. Suppose we know our problem we're dealing with is the square root of x squared minus 25 over x dx. Don't worry about the x, don't worry about the dx, we'll take care of that here pretty soon. All we're concerned with, whenever you have the square root of squares being subtracted, or the square root, if this would also fall in this category if this is plus. So this could be either the sum or the difference of squares inside of a radical. That's the indicator that trig substitution is going to be your first pitch. If you have a square root of either two squares being added or subtracted, that's how you know you're doing trig substitution. All right? If this had been the square root of x, and we have the square root of x minus 25, in the strictest case, this still could be done, but this might not be the pitch you want to take because this isn't a square. Or suppose this were x squared minus, let's say, 2x. As it currently stands, this is not a trigonometric substitution. It turns out we can do something to this and force it to become, but we'll push that down the road for now. So what we're looking at now, the scenario we're identifying this, is square root of either the sum or difference of squares. All right? First thing is we need to label this triangle. If you label this triangle takes you down the path that you need to go. If you don't use the triangle, then really what this becomes is a memorize contest. If you want to do that, God bless you, have at it. But this is the way I learned this, and this is straightforward. It never fails. It always takes you down the same path. So, as soon as you know you're in trig substitution, draw the triangle and label the triangle. Now, there are rules of thumb when you label a right triangle. We knew this from basic geometry. We remember it from basic trigonometry. Whenever you label a right triangle, rule number one, the first thing you label is the hypotenuse. Always, the first thing you label is the hypotenuse. So the question is, in which one of our scenarios are we here? If this is square plus square, then the hypotenuse is the entire radical. If this is square minus square, do you remember the rule? If this is square minus square, then the hypotenuse is this first square root. So in this case, x is the hypotenuse. All right? In this first case, x is the hypotenuse. Now, the next thing, always, this is my rule of thumb that will take you down the same path every time. There are ways to get around it, but this rule will take you down the same road every time. You'll become familiar. It becomes part of your mental furniture. Always, if possible, make the variable the vertical. If possible, make the variable the vertical side. Variable, vertical. Variable, vertical. If possible, make the variable vertical. Well, the variable's already spoken for. All right? So what two choices do we have left? We know that from this triangle, one of the sides needs to be x, one of the sides needs to be 5, and one of these sides needs to be the radical. We know the three sides of our triangle here are x and 5 and the square root. So the question is, which side gets labeled the variable? If possible, use the variable for the vertical. Well, if the variable is already spoken for, then our rule is use as much of the variable as possible. Use as much of the variable as possible. So what's left over here? What's left over is the 5. And so we've labeled our triangle correctly, and we can go from there. All right? So what I'm going to do now is we'll leave this for now. We'll come back and do several more examples of this, just getting the triangle correctly labeled, and then we'll come back and do several examples of that.